Alrighty, so today we are going to continue our discussion of electrodynamics, and specifically we're going to cover a topic that actually extends far beyond just this particular subject and is useful in many areas of physics, classical mechanics, quantum mechanics. It pops up a lot. It's actually a technique for differential equations specifically. So the way we'll get to it is by posing a question. Here's a problem. Let's say we have a situation, three-dimensional problem here, and we're going to have an infinite sheet that is right here. And let's say actually we'll let this be this will be x, this will be z, and this will be the y direction. So we have a sheet down here in the xz plane. That's at y is equal to 0. And then we'll have another sheet up here, similarly. And this sheet is at, let's say, y is equal to a. So these are conductors, metal sheets, and what we're going to do is we're going to force these conductors to be at a potential of 0. So we've got those two metal sheets, conducting sheets I should say. One here, one on top of each other like this, separated by a distance a. And then we're going to place another, let's say, band. And by the way, like I said, these go off infinitely in that direction and that direction. We're going to put a little, let's say, band between these sheets right here, but only on the left edge. Okay? And that band, again, this extends off that way as well, is different than the conducting sheets in that this is some kind of an insulator, let's say, or a material that allows you to put charges on it, and the result is that this green band will have a functional form of its potential. So its potential will be some kind of a, let's say, a function of y. So as you go up the sheet that way, the potential is changing. But as you go this way, the potential is the same at the same y location, right? So you have a band of potential of some amount here, and then some different amount there, and some different amount there. Very general, because we want to do this problem more generally first, and then we could specify some functional form of the potential. Maybe it's constant. Maybe the potential is everywhere V naught. Or maybe it increases linearly with y. So the higher up you go, the stronger the potential is. Or it's sinusoidal, or whatever. It's got some functional form. We don't know what the functional form is. But we do know that it only depends on y. It has no z dependence. Nothing here has a z dependence. But obviously there is some x dependence, because as we go out here somewhere, let's say we're looking over here at the potential. That's what we're going to want to find. What is the potential at this location? Well, we're further away from that green band than if we looked over here. Over here, we're closer to it, so we're going to feel a stronger potential there. But more to the right, more to the positive x direction, it's going to die off weaker and weaker as we go. All right, so the question will be, find the potential everywhere between the conducting sheets. That's the question. Now, what we know is that in order to calculate potential, we have to use Laplace equation. So the Laplacian of the potential is equal to 0. And generally speaking, if we're doing Cartesian coordinates, the Laplacian is just the second derivative of the potential with respect to x squared, plus the second derivative with respect to y, and the second derivative with respect to z equals 0. So that's what we have to solve for in this situation. With these boundary conditions, you know, the potentials are 0 on the gray sheets. The potential is a function of y on the green band. And there's no z dependence. So the first thing we know is that because there's no z dependence, we don't need to worry about that. This is really more like a two-dimensional problem. Because for any value of z, as we go out of the page, out of the screen towards you, or into the page, away from you, whatever value of the potential we had here is going to be the same there, and then further away and further away in the z direction, because it's symmetric in the z direction. So really we only have x and y dependency, so we only have to worry about this as if it's a two-dimensional problem. So we say, okay, let's try to solve this problem. We have this differential equation. Second derivative with respect to x plus the second derivative with respect to y is equal to 0, and we want to solve the potential for this particular system. Well, how do we solve this problem? This is where this technique is going to come in. What we're going to do, and this doesn't always work for every single differential equation, but it is a tool at your disposal to try to use and see if it happens to work. What we're going to do is we're going to say, let's assume that the potential, which here is only going to depend on x and y, because like I said, the z dependence is, there isn't one, it's symmetric in z. We're going to assume that this potential can be written as the product of two functions. One function only depends on x, and one function only depends on y. Okay? Now, it doesn't have to be this. You know, we could have all sorts of things. We could say this is e to the x squared y times y plus, I don't know, 2x minus y, something like this. Can I write that function as the product of two functions? One is only dependent on x and one is only dependent on y. Very, very few functions actually can be written like this, but it turns out that those functions are usually pretty important for us. But let's see. Let's try it here. If I were to assume that this is true and plug it into my differential equation, what happens? Well, I have the second derivative of v, but v is x times y with respect to x squared, plus the second derivative with respect to y squared of, again, x times y. And remember, this isn't little x and y, the directions. This is big x, big y, the functions. And I'm later on going to try to find what are these functions. But Laplace equation becomes this. Now, how is this useful? All I did was rename v. V is now just called xy. Okay, who cares? Well, the reason this is useful is because since x is only dependent on x and y is only dependent on y, notice for this first term, this y piece of the function is going to act like a constant because these are partial derivatives. The only thing the derivative is going to hit is the x piece. So I could actually take it out of the derivative and put it out in front. And same thing over here. This x piece is not going to get hit by this derivative, so let me just take it out front. And so now this looks like y times the second derivative of x with respect to x squared plus x times the second derivative of y with respect to y squared is equal to 0. All right, still not perfect, but now what are we going to do? And here's the big trick. Now we're going to divide both sides of this equation by xy. And what happens when we do that? Well, we had this, squared x by dx squared, plus x d squared y by dy squared equals 0. And I just divided by xy, so I divide this by xy, divide this by xy, and of course the right side is just 0, so that doesn't matter. And now, once we've done that, notice the y's cancel here, and the x's cancel here. And so now what we have is 1 over x d squared x by dx squared plus 1 over y d squared y by dy squared equals 0. And now this is very nice because notice something we have here. We have one term which only depends on x. There's no y dependence at all there. And this other term only depends on y. So if I rewrite this, I move the y piece to the other side maybe, I'll have 1 over x d squared x by dx squared equals minus 1 over y d squared y by dy squared. And this is important because the only way this can be true, since x only depends on x and y only depends on y, they're independent of each other. The only way for any x, let's say I choose an x function, I choose an x value, and then I can vary y however I want, and no matter how I vary it, these will always be equal. And same goes the other way. I could choose a value of y, set it, and then vary my x, and no matter what x I choose, these will be equal again. The only way this can possibly be true is if this side is equal to some constant, let's say alpha, and this side is equal to some constant. Right? That's the only way this can be true. That if some function of x, and only x, is equal to some function of y, and only y, and x and y are completely independent of each other, the only way they can always be equal for all values of x and y is if they're both constant. All right, well, if that's true, then we've just reduced our problem here into something very easy. Let's take this piece first. This piece says, let 1 over x d squared x by dx squared equals some alpha. Well, move the x to the other side, so I get second derivative of x with respect to x squared is equal to alpha x. And we know how to solve this differential equation. We've seen it before. We take two derivatives of some function, and what happens? We get the same function back times some constant. What function do you know that when you take its derivative some number of times, you get the same function back again? Maybe times a constant. Well, that's the exponential function. So this implies that x, the function we're looking for, which is only a function of x, must be some a e to the, let's say, alpha x. It's actually square root, so here's a little trick just because we want to avoid square roots and stuff. I'm going to call this alpha alpha squared. A constant, I could just write it as some other constant squared. You could always do that. And the reason is because when we take two derivatives, the first one brings down one of the constants. The second derivative brings down the same constant again, so they multiply. So that'll be some alpha squared. So e to the alpha x plus b e to the minus alpha x. That's the solution for the left side of the equation. Okay? Again, because the x stuff for all values of x always equals the y stuff for all values of y, the only way that can be true is if the x piece and the y piece are both constant. So if they're both constant, let's solve one of them for the constant. And that's what I did here. And then we're about to solve the other one for the constant too and figure out what the functional form of y should look like. And then we go back to our original assumption, which said that the actual thing we want, the potential, is just the product of x and y, and we'll have our full potential. And again, the little trick I did here was I called the constant that this function, this differential equation is equal to, alpha squared instead of alpha. And in fact, let me just go ahead and write them here too. I could call it alpha to the 1/3 if I want. Doesn't matter. It's just a constant, some number. But I call it alpha squared because it's useful, so I won't have square roots in my exponential. That's the only reason. All right. So there's the x piece. Now I'll take the y piece and go right here with it. And this says minus 1 over y, second derivative of y with respect to x squared, is equal to some alpha squared. Okay, well, we'll do the same thing. Let's move the y over. And so I get the second derivative of y with respect to y squared is equal to minus alpha squared y. All right, so here we go again. Being physicists, we're going to guess the answer instead of just trying to actually solve it. We need some function whose second derivative gives back the function again, but with a minus sign now. And there's also constants involved, but constants are fine. So for the x piece, the second derivative gives back the function itself positively. The y piece, the second derivative gives back the function itself, but times a negative. So exponential won't work. At least not the real exponential. Complex exponential will, but. So if it's not exponential, what about sine and cosine? Well, I take the derivative of sine, and I get cosine. And I take the derivative of that, gives me minus the sine. So indeed, I had sine to start with. I took two derivatives, and I got minus sine at the end. So sines and cosines work for the y. Y, which is only a function of y, must be some c, let's say cosine of alpha y, plus d sine alpha y. And now I have the functional form for my y equation, or my y function, I'm sorry. All right, well, now that I have those two, I look back here at the assumption I made, which was the actual potential, the thing I want, is just x times y. So v, which is x times y, is equal to a e to the alpha x plus b e to the minus alpha x times c cosine alpha y plus d sine alpha y. And that's my potential. However, I'm not done with the problem, because if you remember, all I did was solve Laplace's equation in general. What makes this a specific problem, or a more specific problem, is I have to go back to the problem itself and look at the boundary conditions and the initial conditions, things like this. That's what really defines this problem versus some other problem. Maybe some other problem has a spherical shell of conductor somewhere, or a hemisphere, or maybe the plates are not aligned horizontally but vertically, or something. So this specific problem is defined by its boundary conditions. And what were the boundary conditions for this problem? I'll write them here first. Well, first, the first boundary condition said right here that the potential is equal to 0 at y is equal to 0. Right? This gray plate is in the xz plane at y is equal to 0. So for any value of x, any value of z, if you're at y equals 0, the potential is 0. And likewise, the other one says v is equal to 0 at y is equal to a, the top plate. That top plate is 0 everywhere as long as you're at y is equal to a. So let's go ahead and insert these boundary conditions. I'll put them right here. Boundary conditions. The first one said v is equal to 0 at y equals 0. Okay, so I just write my potential, v, which must be 0. What is the potential? Well, it's a e to the alpha x plus b e to the minus alpha x times c cosine of alpha y, but I'm setting y is equal to 0. Y is equal to 0 there, plus d sine of alpha y. Y is equal to 0 here. All right, so what does this tell us? This tells us a few things we have to be very careful about. Firstly, sine of 0 is always 0, no matter what, so that just goes away. Cosine of 0, that's just 1. What else is important to understand here? Well, we need to be careful that when we look back at our problem, think about what I said at the beginning. If I'm looking here at the potential, I'm some distance away from that green band. Okay? So I'll have some potential, something, whatever it is, some number. But then if I stay in the same y height and the same z distance, but I just move over to the right some distance in x, I'm now further away from that green band. So I expect my potential to go down. The further I move off in the right direction, in the positive x direction, the lower and lower this potential should get. In fact, as I go to x is equal to infinity, the potential should go to 0. I'm infinitely far away. So if we look at our potential here, when x goes to infinity, what do we know? Well, this term here is fine, right? If I put x is equal to infinity, e to the minus infinity is 0, that just goes away. So that's 0, perfect. However, this term here, when x is equal to infinity, it blows up. It gets bigger and bigger. So I know for sure this term has to be 0 when x goes to infinity. And the only way for that to be true is if a is equal to 0. So when x goes to infinity, that term better go to 0. How does it go to 0? Well, the only way to do it is to make a, that constant, and it's always a constant, it's always the same number, that better be 0 always. So that term must go away as well. What do we have? We have b e to the minus alpha x times c, right? The d term went away from this thing, and all of this is still equal to 0. So how can this thing be equal to 0 always? Well, the only way this could be equal to 0 always is if either b is equal to 0, but no, we're going to leave that alone for now, or c is equal to 0. And indeed, that's the one we're going to set. This is equal to 0. So we've learned from this boundary condition specifically, c must be equal to 0. Now, the other thing we learned was the a is equal to 0, but that's not because of this boundary condition specifically. That's due to a physical principle that must be true. And you'll see this if you do quantum mechanics. Same kind of a thing holds when you do, let's say, the, what do we call it? The standing wave solution, or you're finding a wave function maybe for a free particle or whatever it is, or finite square well, or all sorts of different potentials, you're going to get exponential functions. And one of the things you have to use as a, quote, boundary condition, but it's more of a physical principle, is that the wave function must go to zero at infinity. The wave function must die out at infinity. And this is not like a written down boundary condition like the one I wrote down here, which is the potential is zero at y is equal to zero. It's more of an implied boundary condition. You just have to remember. And so that boundary condition told us that when x goes to infinity, this potential better be going to zero, and the only way that can happen, because the b term allows it, when x is infinity in the b term, that's fine. But the a term, he doesn't go to zero when x goes to infinity. So the only way to force him to go to zero is to set a is equal to zero. So we know a is equal to zero here, and c is equal to zero due to this boundary condition. All right, so now what do we have? V. Well, we still have b e to the minus alpha x times d sine alpha y. That's what our potential is now. Because the other two terms we've found out must be zero due to the boundary conditions. Well, we have another boundary condition. When y is equal to a, the potential must be zero again. Right? That's the top plate. We did the bottom plate boundary condition. That's y is equal to zero. The potential goes to zero. Well, now for the top plate, it's also zero. And the top plate is at y is equal to a. So, okay, we've got b e to the minus alpha x d sine alpha a must be equal to zero. All right, so how does this help us? Well, again, this is something you see in quantum happen a lot. What we want is for this term to go to be forced to be zero when x or y is equal to a. So when is d sine alpha a equal to zero? That's when, and we don't want to set d equal to zero, because if we set d equal to zero, we've lost all of our y dependence. We had two things in our function, our answer, that depended on y, two terms. Well, we just lost one of them because c is equal to zero. So the only y dependence we have left is the d term. So if I said d equal to zero, well then the whole y dependence goes to zero. And same for the b. I can't set b equal to zero because then the whole x dependence goes to zero, goes away. So if y is equal to a, and we need this thing to be zero, the only way that can happen, well, it can't be something in the exponential because the x can be any number. Like, you know, you can't set that to be zero unless you make b equal to zero, but we're not doing that. So the only way this could be true is if sine of alpha a is equal to zero. If sine of alpha a is equal to zero, we're still going to have our d dependence, our y dependence there, but for the special value of y, that piece will go away. So when is the sine function equal to zero? Sine of something equals zero when theta, that's something, is equal to n pi, right? When theta is zero, sine is zero. When theta is pi, sine is zero. When theta is 2 pi, sine is zero. So any n pi, any integer multiple of pi, will make the sine function go to zero. So that means the something, for us, alpha a, better be equal to n pi. So this implies alpha then must be n pi over a for integer n. So once we've discovered this, what do we have? Well, our potential was b e to the minus alpha, but we just found out what alpha is. Alpha is n pi over a. So n pi over a times x times d sine of alpha y. Alpha, again, is n pi over a times y. And now we could just combine b and d together because they're both just constants and they're multiplied by each other, so you get a different constant. So we have some constant. I don't know what we could call it. Let's call it eta, whatever. Better eta than that. There we go. Eta e to the minus n pi x over a sine n pi y over a. And now we have our potential. Notice it's got x and y dependence. They're the products. That's exactly what we made the assumption of before, and we kind of forced it here. And now what we would do is if we had a specific problem, because you remember, although this was more specific than the general Laplace, I did not specify anything about this green band except that it depends on y in some way. So, if we had a specific problem, that problem would say what this dependence is. This y dependence is some such thing, maybe it's a constant, maybe it's linear in y, whatever. Once we know that, then we could use that information to kind of whittle down this answer even more. For certain values of y, you should get certain values of the potential, and we could solve for eta or whatever it is we want to solve for here. So that's separation of variables. It's a very, very powerful technique for when it can be used for solving these differential equations. And the way it works is you have your differential equation, whatever it happens to be. In this case, it's the Laplace equation. And you're going to assume the solution has a certain form. And the form we're going to assume here is that it's the product of the two independent variables in some way. Or it's the product of functions of the two independent variables. So I know the potential only depends on x and y. So I'm going to say the way it depends on x and y is that it's the product of some function of x. It turns out here it becomes the exponential function, and some function of y. Here it turned out to be the sine function. If we had a more general problem that had all three dimensions, x, y, and z, then we would assume v, if it depends on x, y, and z, is the product of x times y times z. Capitals, the actual functions, not the dimensions themselves. Once you assume that, then you stick it into your differential equation, explicitly showing this product dependence. Then you factor out, or you pull out from the derivative those pieces that won't be hit by the derivative because they're only dependent on the other variables. And then you divide the whole equation by the potential itself, or by the function itself, which means, in this case, I divide it by xy. In a three-dimensional case, it'd be divided by x, y, z. And what that does is it cancels out all the wrong dependencies and only leaves the dependency that goes with your derivative. Here, the first term is a derivative with respect to x, but there's a y dependence on the outside. When I divide by xy, the y cancels out, and I'm left with just the x dependence. So I have an x, 1 over x, times the derivative with respect to x. And the same would be true on all the other terms. Once you have that, you have the sum of terms, but each term only depends on its own individual independent variable. And the only way for the sum of these independent functions of independent variables to always be equal to 0 for all values of those variables is if each one of those terms is equal to a constant. Once you know that, then solve each one of the terms independently of each other, get their solutions. Then, once you have all the solutions for each one of the terms, you go back to your original assumption, which was that the solution, is the product of these terms. So there's your general solution. Then, at that point, now you start using the boundary and initial conditions from your specific problem to start whittle away at these coefficients, the A, the B, the C, the D, whatever. You use your boundary conditions. In this case, for instance, the bottom sheet has potential equal to 0 for all values of x and z when y is equal to 0. So we set y equal to 0, set the potential equal to 0, and then we see what naturally goes away. Those are good terms. The terms that don't naturally go away, we have to force them to go away. And the way we force them is by setting their coefficients to 0. But you have to be careful because you could go too far with that. We could have done it here too. Sorry, this should have said y is equal to a. Y is equal to a, v is equal to 0. Here we could have set the d coefficient to 0, and that would have solved this. The problem is, if you set all your coefficients to 0, then your answer is just 0. You don't have a function anymore. You have to keep the function. You have to keep these dependencies somehow. So the only way, for instance, for this boundary condition to work is if not the coefficient is equal to 0, and not the x-dependent stuff, because the x-dependent stuff is its own thing, but rather the functional form, the sign part, must be equal to 0 for this special value of y. And that is, the sine of some theta is equal to 0 when the theta is n pi. And so whatever is inside the sine, set it equal to n pi, solve for your other unknown, which this unknown was the alpha I started with way back here, this alpha thing. That whole time I had no idea what the heck is alpha. It could be 4, it could be 7 pi, I don't know what it is. Well, this boundary condition sets what that alpha can be. It must be some integer multiple of pi over a. Once you do all your boundary conditions, you're left with whatever terms you didn't mess with. That's your answer. So, I hope this was helpful. If you have any questions, of course, just let me know as usual, and I'll see you next time.